Shall we start by building our list?
Can we go over this? Because I didn't know.
Question number 1.
Yeah.
How to prepare an alkyne?
Yeah.
Sure. Do you want to be that?
Like I just didn't know because I didn't understand which one it was.
That question in particular or that concept?
This full. Maybe,
Okay.
But this one I just didn't know what the answer was.
Sure.
I didn't retake it because I don't know what it is.
All right, so let's say that I want to make this alkyne. And the question is saying, what can I react with a strong base to give this alkyne? And we'd need 2 equivalences of our strong base, which should remind you a little bit of our worksheet. Right after the 4th unit test, we were talking about alkynes, ways to prepare alkynes, and we said things like what dihalides could be a precursor to this. When we talked about learning alkynes, we said that geminal dihalides can be eliminated to alkynes, but so can vicinal dihalides. If they're geminal, then it's that carbon will be a part of the alkyne, and either the one on the left or the one on the right, which was backwards for you guys. Or if they're vicinal, it is those 2 carbons that will become the carbons of the alkyne. So let's just map these so that we have an idea of how long our carbon chains would be. Okay, well, if I wanted a geminal precursor, a geminal dihalide precursor, then I could have the geminal dihalide be on either carbon 1 or carbon 2. Because I need carbon 1 and carbon 2 to be involved in the alkyne, so either one of them could have been a geminal dihalide holder. It doesn't mean that it's the only alkyne that will necessarily form, but this alkyne definitely can form from these dihalides. Plus, if there's a vicinal dihalide across carbons 1 and 2, that will also form the alkyne in the position that I want.
I think is there any correlation between the substitution of the carbons? Because when I looked at this question, I kind of looked at our chart that had S and 2 and looked at the substitution of the carbons. Is there any correlation there? Or
not as much. You might have noticed that when we learned how to form alkynes, which was before we had these words E1 and E2, SN1 and SN2, we used this strong base, sodium amide and sodium hydride. And do you know what we didn't list in that table when we were learning about substitution and elimination? We didn't list sodium amide as a base or nucleophile. We didn't list sodium hydride as a base or nucleophile. They behave differently from our other bases. So for your context, we could say that they're pretty much reserved for the elimination of our dihalides to alkynes, or for the deprotonation of the terminal alkyne to make a nucleophile. Okay, so if you were looking here and you're saying primary halide can't do E2 unless I have a big bulky base, right? So that was your reason for ruling this out.
yeah.
Because it would have a preference for SN2. So my argument would be, yeah, but this isn't a base that I told you to worry about with E2 SN2 competition. But I do see what you're saying. Do you guys see this as well? The idea that a primary carbon has very little steric strain. Primary carbon, primary, primary. And by not having a lot of steric strain, it allows nucleophiles to just come right in and bond to the carbon substitute out another group. But it is still a plausible precursor for our alkynes. Yeah,
That makes sense.
I think that question is based in really sound logic, which is a great question to have.
Thank you.
By the way, we have 2 days of review. So if we make a list now of general concepts or specific questions, then whatever we don't get to today, we can come back to on Wednesday. And sometimes I forget to actually build the list, and we just dive right in. Oh, I should also say this. The STEM Center is hosting a final exam review for OChem 1 next week, Tuesday, which is not an ideal time for any of you because your exam is next week, Monday. So my recommendation is go to the STEM Center after class today and Wednesday. Johnny Pope tutors until the STEM Center closes both of those nights. And he is probably the one that would have been hosting the OChem 1 review anyways. So he has access to my past material. He can answer questions and guide you guys through problems. But if you see signs for the STEM Center's review session, just know that it didn't work out in the timing for us. Okay, a list of things to do. What do you guys want on this? Britton. Radical halogenation. Tanner.
I want to go over question 10 on the final.
Question 10 on the fall 25 final. All right.
We talk about for example, on our test this weekend, like when you're given a reagent and a product, kind of to just some tips and tricks to figure out, okay, is this like SN1, SN2, or E1 versus E2?
Mm-hmm. Yeah. How do you distinguish between what type of substitution? And quickly, what is the main difference between SN1 and SN2? Steps involved. Yeah, they have different number of steps. Anything else? Yeah, one of them has a carbocation intermediate, which is important and quite different from a reaction that doesn't have a carbocation intermediate. But yeah, we can, if you have starting material and product, how are you supposed to figure out whether it's SN1 or SN2? How do you figure out whether it's E1 or E2? We can talk about that. Layla.
I feel like that's some of the questions there were like solvents involved.
Hmm.
Like, I think the online work and then the solvent played a role sometimes. And I was a little confused. Because like it's either codec or acodec, and that for some reason teaches you something or something. I don't know.
Yeah, I do not really lean into the distinction there between whether you're doing SN2 polar protic or whether you're doing SN2 polar aprotic. If we wanted to, we could take a Gen Chem 2 look at kinetics in these reactions. For instance, I got away from this because I don't ever see any chemical syntheses being reported where they're doing this. But you can take something like iodine and you can substitute it for bromine, which means that I would need iodine to be the leaving group and I would need a bromide ion to come in and be the nucleophile, right? And I could either run this reaction in a polar protic solvent or in a polar aprotic solvent. And which one would it run faster in? And then we could actually compare the different halides. How does chloride compare to bromide compare to iodide in polar protic versus polar aprotic? And it's an interesting conversation, but it's a lot textbooks will talk about this a lot. I've seen classes that have this be a big thing. Which is a better nucleophile in what type of solvent? And I don't address it much. So on active, I don't think you saw any that were kinetics based, but you maybe did see that they simply provided a solvent. I don't go over it because I've not seen people in materials chemistry, pharmaceutical chemistry, medicinal chemistry, trying to swap out one halogen for a different one. It does introduce a conversation about how the solvent interacts with the reagents, but not one that I have found useful enough to take our time in class away for. Do you have specific questions, though, that really hit on the solvent? I did tell you guys earlier in the semester, I'll show you halogenation, and I won't show it with a solvent. I will show you halogenation just Br2. But on active, you might see it Br2 with THF. And anywhere that you see a chemical change, and the only difference is that there's this solvent added, that solvent is doing nothing. Its job is to do nothing. It is just there to dissolve everything. So I don't take the time to show it, but active will throw them in. Other places online you see will do it too. It would do nothing. Yeah. If you had an arrow pushing step that said THF is added here, it would play no role. Okay. What else can we add to the list? Hamza.
Can we go over question 34 from the old final?
You got it. What else?
Question 31.
Question 31. What else? Oops. Vivi. Yeah, on the practice final? Okay. Did I see your hand raised?
Yeah. For the alkyne reactions, do you remember how you were like, we need to switch those two? I felt like over the weekend I really had to pray about that, but I just want to make sure that I have like written down correctly. We can just make sure we identify like,
Yeah, thank you.
Thanks.
Vivi.
Top of that, like which ones you recommended we know?
For arrow pushing.
For that, like, I know you had pointed out specific ones for the alkyne reactions, like what we should know.
I won't ask you to show arrow pushing on alkynes.
Oh, no, sorry, like the alkyne reactions, like on that paper, I thought you had specific ones that we should know.
You should know all of the reactions. Yeah, I have taken out reactions that I don't care for you to know, but all of the reactions I showed you guys throughout the semester are reactions you should know for the final. So it's a small list, like 30 reactions. You guys are studying for anatomy. How many foot muscles do you have or whatever, right? Like this is a small list in comparison to some things. Foot muscles. I was actually thinking bones. There's a lot of bones in the feet, right? What else can we add to this list?
Can you do like multi-step synthesis? I feel like we like kind of touched on it.
And we never solved those problems that were on the end of your worksheet. Did you guys try your hand at any of those multi-step synthesis problems? So we could do some of those practice problems. Okay, what else? Camilla? Yeah, I'm going to add that right in there because they kind of go hand in hand. If you have a final product, can you figure out where it came from? And if you have a starting material, can you figure out where it goes? And a lot of times meeting in the middle is super useful. We can keep adding to this list as well as we go.
Question 27.
On the practice final?
Yeah.
I knew I was going to need more space there. I'm glad I left it. Okay. Well, here's one that we can start with then. On the worksheet from last week, I gave you guys a multi-step synthesis challenge. It said synthesize, I might be rewording it a little bit. Synthesize methanol from methane. When you're doing a multi-step synthesis, I have 3 tips. One is map your carbons. Well, methanol, CH3OH, and methane, sorry, did those backwards. There's just one carbon involved, so I don't really need to map my carbons at all. I do know that I'm not doing any alkylation with an alkyne, right? I'm not extending a carbon chain by any means, and I'm not losing my carbon. My other tip is brainstorm. What reactions are possible? Well, we've seen ways to make alcohols. We had alkene hydration reactions. Our alkene hydration reactions could add Markovnikov, anti-Markovnikov with a carbocation, without a carbocation. But those were alkene addition reactions, and there is no alkene precursor that could come from this. So I don't think I'm going to be doing an alkene addition reaction here at all. We've also learned how to do reactions with alkanes, and that's what methane is. It's just an alkane. Do you guys remember what reactions are allowed on alkanes? Just one. Just radical halogenation. It's a substitution reaction. And to be fair, that's not entirely true. That's just the only reaction I give you. Actually, your body has ways to do dehydrogenation. Your body can do an elimination on an alkane and pull out 2 hydrogens. But to my knowledge, chemists can't do that very easily. Chemists can't take an alkane to an alkene, but chemists can take an alkane to an alkyl halide. So one thing I might be able to do here is radical halogenation. Because that's the only thing I can do with an alkane. So I'm doing brainstorming right now. What are the things that I know that I can do? I know that I can do radical halogenation. The other tip that I give is work forward and backwards. We already did some of that trying to work backwards with our brainstorming, like what things can I do that lead to alcohol? But now it's time for me to really just start going towards it, because I know there's only one thing that I can do from my starting material: radical halogenation. What would be reagents that I add for radical halogenation? Light is one of them. We'll write that as H nu. Yeah, with our radical halogenation, we're going to selectively use bromine. In theory, you can say any halogen, but bromine works the best. And it's a substitution type reaction. It's not SN1, it's not SN2 by name, but it substitutes a hydrogen for a halogen. Now I might need to go back to brainstorming. What can I do to get bromomethane to become methanol? Well, that would be a simple SN2 reaction. Do you guys agree that we know how to make alcohols from alkene addition, but we also know how to make alcohols now by substitution? We said that if I have water, water can act as a nucleophile and lead to an alcohol. Hydroxide, the conjugate base of water, can make a nucleophile. Could you give a reagent that would solve this synthesis? Hydroxide solves this. Is hydroxide the only thing? What else could work? RO minus. If I took RO minus, and let's give R a name, let's call R methyl. RO minus leaves me with an OR group. So RO minus would not work. Not to make methanol. RO minus would work to give an ether.
Is it ROH?
ROH would actually do the exact same thing. So again, ROH here would just be, if R is methyl, then we're saying methanol. The distinction between RO minus and ROH.
Oh, sodium.
Sodium. One has got a counter ion. And it's a strong nucleophile. But ROH, just a regular alcohol, is a weak nucleophile. The distinction here is whether it's good at being a nucleophile or not good at being a nucleophile. The distinction is not what functional group I form. I'll form the same functional group no matter what. The distinction is how good it is at donating its electrons. So the other reagent that I could add here and still get methanol NaOH would be a form of OH minus. If I can substitute using RO minus to make an ether or ROH to make the same ether, then I could substitute with OH minus or water, H2O, to make the same alcohol. Alcohols are formed by reactions with water. Alcohols form ethers. Alcohol is the precursor to ether, and water is the precursor to alcohol. Say that one more time. Water is the precursor to alcohol. Alcohol is a precursor to ethers. Johnny, does this work?
No, that's why I came in here.
Oh no.
Well, because you guys already have your final Monday, right?
Did you read it though? I'm just telling them to come to you after class on Wednesday.
Oh yeah, I mean they can. Oh, like today's not Wednesday.
It's not.
Yes, so yeah, you can do that. What I'm also trying to do is see if I can schedule a different review workshop that's not after your final.
Yeah.
So.
Sure. But if a horde of them came on Wednesday after class,
If a horde of you guys do come in, then I can basically just make it a workshop, probably. But yeah, so I'm trying to see if I can get something for Friday as well, maybe before my OCHEM 2 workshop.
okay.
And also maybe if they can just let me come in on Thursday or something instead. They haven't gotten back to me yet on that.
Yeah.
But I'll see if I can do that, because that's not very helpful workshop time.
No, but this is one section out of, I don't know how many,
Yes,
3 or
but
4.
Also, your sections are usually 90% of the attendance. So
Strange. I don't know why that
I
is.
think you just advertise it more.
Oh, maybe.
Or you're a really bad teacher. Now you know, whichever one you prefer. Okay.
Thank you, Johnny.
Also, I am here until 9 today as well. If you guys want to come in after your class, which I doubt, and I don't blame you, but you're all gonna come in later as well.
Thank you. All right. Does this make sense?
Is that an SN2 reaction then? Is that what that would be?
On methyl carbons,
No.
there's only SN2.
Oh yes. Okay, so that's why we could use water or the OH minus even though they're different. Like water's not.
A weak nucleophile doesn't always drive SN2 because it's not good at being the nucleophile. SN2 does not have a carbocation intermediate, correct? SN2 has a nucleophile basically evict the leaving group. The reason the leaving group leaves is because a nucleophile has come in. So it's best if you have something that is good at coming in. And remember that these are all just magnets, right? So the stronger the charge on your magnet, the stronger the magnet, the better it's going to come in and evict the leaving group. Less charge, less magnetic, less good at doing all of that eviction stuff. But on a methyl carbon, the carbocation does not form. It's too high in energy. It takes way less energy just to do SN2. So for this carbon, we could use water or hydroxide. Although they have different strengths, they give the same final product. And these would both be SN2, but they would have a different number of steps. Hydroxide would substitute in one step, it's done. Water would substitute and then need to be deprotonated, and then it would be done. So there is a distinction between SN2 is not always just one step. Sometimes there's a little acid-base chemistry that has to happen as well. SN1 is sometimes 2 steps, but a lot of times 3 steps because it needs a little acid-base chemistry as well.
And then the excess water would just deprotonate that, right?
Mm-hmm. Yeah, you're essentially running it in solvent, and the solvent would act as that base.
Okay, so maybe a silly question, but a nucleophile donates electrons, right?
A nucleophile donates electrons.
So what does it donate to? Like, where do they go?
They go to the electrophile. If we look at MO theory, MO theory says that there is a sigma star orbital on the carbon to bromine bond. And for right now, I'm just going to sketch in the hydrogens that are here. And hydroxide has a hybridized orbital that holds its lone pairs. When these orbitals overlap, we are putting electrons, donating electrons, into the sigma star orbital of CBr. Sigma star. And now hydroxide is putting electrons into sigma star, meaning carbon and bromine don't realize they're bonded anymore. The energy that these electrons are at cancels out that stabilizing energy that the original electrons were at, causing the electrons to drift back to bromine, who is more electronegative and has a larger orbital, so the electrons are more likely to be there anyways. So when we say a nucleophile is donating electrons, the nucleophile donates to the electrophile, and typically it donates into a sigma star or a pi star. It donates into an anti-bonding orbital. Don't you love MO theory? Isn't it kind of pretty though? Big green orbitals. Okay, did that answer your question? Do you get what I'm trying to say when I tell you that water is a precursor to an alcohol? If you want to form an alcohol, then water is a reagent in your starting material. But if you use an alcohol as a reagent, you will form an ether. What I want you to notice is that the OH bond in both cases is removed because the OH bond is easy to remove. But the carbon to oxygen bond is not easy to remove. The carbon to oxygen bond is quite strong. So we don't break the carbon to oxygen bond. If an alcohol is involved in my reagent, you can bet that that carbon-oxygen bond will be preserved in the product. So if I start with an alcohol, I will get something that is not an alcohol but still has the carbon-oxygen bond, an ether. We noticed the same thing back early on in the alkene addition reactions. Br2 with an alkene adds 2 Brs. Br2 with water adds an alcohol in Br. Br2 in an alcohol adds an ether and a Br. Okay, so the idea of finishing this synthesis and figuring out here what is allowed and what is not. Well, it's a methyl carbon, so any of my nucleophiles will do SN2, and I have 2 different nucleophiles that give me the same final functional group. Great. Okay, we talked a little bit about multi-step synthesis, a little bit about substitution, a little bit about halogenation, but let's step into another radical halogenation question so that we can see the distinction. Methane is pretty simple. You guys are all right if I erase this on the left? What happens if I try to run radical halogenation on something a little bit bigger? A bicyclic structure. With methane, it was very easy to predict that we'd get bromomethane. I just take off a hydrogen and put on the bromine there. But the question here becomes, which hydrogen will bromine substitute? Question, answer.
The most stable, where the radical will be.
Good. The bromine will substitute wherever the radical will be most stable. The bromine will take off the hydrogen wherever it requires the least amount of energy to take off that hydrogen. And where will it take the least amount of energy to place a radical? On one of the what? The 3 bond carbons. Is that what you said? 3 prime. Tertiary. 3 prime. Yes. One of our tertiary carbons will be the most stable. Why? It's more, I would say almost the opposite. That carbon is more negatively. Well, actually, okay, I think I see what you're saying. We said if it's more substituted, it would have a partial positive versus a less substituted being a partial negative. We did say that with pi bonds if you had an alkene. The reason that a more substituted carbon would be better being more positive is because it's already shielded by all of this electronegativity, or all of this electron density.
Sorry, I'm back.
Tell me.
Does this Friday work for you guys?
What time? Same time.
So, not entirely sure what time yet on Friday. It would have to end at 4, because that's when I'm giving the Outcome 2 workshop, but assuming we can fit it in between the other, like any other workshops, anywhere from like 11 or 12 to 1 or 3, I have no idea, honestly.
Should we do a raise of hands? How many are available on Friday and would go on a Friday afternoon to a workshop.
Cool. Okay, so not Friday. If it was at like 7, then I could. What days do work for you guys?
Thursday.
Thursday. How many of you would go Thursday? Do you
I don't work Thursday, but I can either say gonna do a workshop or I can.
Thursday afternoon?
Thursday night, if that's a Thursday night.
Thursday night.
Any night, yeah.
Any night. Okay. Do you guys want to do Wednesday night while I'm already here, just like right after your class here, or does that suck too bad?
I know it is tough to have to listen to me talk for 2 hours and then go keep working for 2 more hours. But it's a useful, you're already here.
Okay, so it seems like
What are you going to do? Go home and eat dinner and sleep? Come on.
Okay, so Thursday night is looking like it's the best.
Yeah, that got the most hesitant hands for sure.
I will go see what I can do about that.
And just keep me updated. I'll message them all.
Yeah, I will.
Thank you.
Okay.
I have 2 different tertiary carbons, 3' carbons. Where should I place the halogen?
It doesn't matter.
Wouldn't matter. This molecule is symmetric, right? So either one I go to will be the same position. Great.
If we're like drawing it, do you want us to like show the intermediate of the radical or just go straight to the?
So this is a good question. If you're this type of question could come up in the final in a few different ways. One, it could be a multiple choice question. It could be what reagent completes the reaction as shown, or which of the following products is the major product formed, or the likely product, or what starting material would work to give this, or sorry, this would be hidden. What starting material would work to give this product? So it could show up. Another multiple choice question could be, what does the intermediate look like in this reaction? In which case you would want to know that the intermediate has a radical. And how do you know that this reaction has a radical intermediate? The light is actually a good giveaway. Light is a radical initiator. Light is not used for anything else in our chemical reactions. We use light to form radicals. So if you see H nu, you're trying to form a radical. There are some other ways that we form radicals as well. Peroxides form radicals a little bit more readily. So we don't always write that light is necessary with them. But you wouldn't need to show this for a multiple choice question. If this were a roadmap question, and I showed you guys the roadmaps, those are where you've got all of these different reactions happening and you're kind of seeing how they all connect. You also wouldn't need to, because that's just another version of give me a starting material, give me a product, give me a reagent. So there's really no step where you'd have to show me the intermediate, but you might need to know what the intermediate is. Because this is not a question I'll be asking you to show the mechanism for. Did I see someone else's hand go up? Let's hear your question, Britton.
So on the quiz this weekend, this was, I got this wrong, and it was methyl cyclohexane. And it would be obviously your radical halogenation. So with that radical form where that methyl group is attached on that carbon of the ring, then the bromide would connect right there. And so it would be one methyl, one bromo cyclohexane.
Yeah, 1 bromo, 1 methyl cyclohexane.
And then the terbium oxide comes in and creates that anti-state oxygen.
Exactly that. Good. All right, I want to change this a little bit because radical halogenation does not just happen on alkanes. Radical halogenation also happens on alkenes. how do you know that these two reactions are going to give different products? One has light. That's how you know that these are going to give different products. Light changes everything. Light indicates what type of reaction? Radicals. Light is a good indicator that you're running a radical reaction. So in this top reaction, I did mean to have a double bond there, but it looks kind of cute without it. In this top reaction, where is the radical most likely to form? Layla? It wants to be in resonance. Radicals, how come this radical didn't want to be in resonance? No pi bond, no resonance to be conjugated with. But this has a pi bond, which does set up for resonance. So the position that has resonance, allylic. Do you want to define allylic? Adjacent to the pi bond, adjacent to the alkene. So should I place the radical here? Is that allylic? It is not adjacent to the alkene. That is the alkene. So adjacent to the alkene would be this top or bottom position, which again, we have symmetry in this reaction. So it wouldn't matter whether I show it drawn on the top or the bottom. But you said they were in resonance. And resonance means that the radical is not on one carbon or the other, but that MO theory says it's on both carbons. So there is another product that forms in this reaction. Do you remember the suggestion, the tip that I gave, the relationship that they have? Gave it a certain type of name that helps you quickly identify their structures. When I form this radical intermediate, and it forms in resonance, what does the resonance look like and what does the other product look like? Yeah, I heard it.
I studied it after I got it wrong.
And this is what I call 1,3 allylic isomers. And it's 1,3 because that's how resonance often operates. Resonance likes to operate through a 1,3 movement. The pi bond shifts, and whatever the charge is or that extra electron shifts. So here I have an allylic halide, 1,3 allylic resonance, or sorry, 1,3 allylic allylic isomers, shifts the location of my pi bond and the location of my halogen in resonance with each other, so both products can form. What would be the result of this other reaction then? Good. Key point there was consume the pi bond. No more radicals. So no more forming radicals in resonance with the pi bond. This one consumes the pi bond entirely. And if we wanted to show stereochemistry, the two halogens form anti to one another, which means that this enantiomer forms and the other enantiomer forms. Hello again.
Sorry, this is a total shit show.
We appreciate the live updates, I'm sure.
So we can schedule it for Thursday, it's looking like. That being said, we have a jamboree or something going on in the STEM Center.
Oh, yeah.
I actually don't know what a jamboree is. Anyway, so I was told to ask, is this classroom available on Thursday? Or are you teaching in here? Or
I'm not in here on Thursday.
do you know if someone is? Or do you know of any other locations that we could go commandeer?
Yeah, Ron's classroom, the lab space right across from here,
Is that for sure going to be
298.
vacant?
There should not be anyone in there, 292.
Okay.
There shouldn't be anybody in there on Thursday nights.
Wait, you mean the
Oh, is that Raj's office? Yeah,
Yeah, it was Rhonda's office.
yeah,
That
you're
one.
right. Yeah, whatever that is.
Alright, I'll go with them. No, I will let you know if I find out any other updates on where it is.
Thank you.
At this rate, it's gonna probably be in the TV building.
Right.
Yeah, I'll try and figure it out.
All right, are we good on radical halogenation? Sure? You want to see more? Is that what that means?
I can jump you. So the second one would just be R2.
Yeah.
Wait. I might actually just.
Okay. We can come back and do more radical halogenation later if we need to. Are you sitting right on the question? You want to ask it?
I just don't know. I don't get why the pi bond would be low.
Oh, it goes through resonance
So why were you going for low?
because there's no resonance down there.
Okay, fair. Okay, got it.
So we are saying that this radical is sitting in a p orbital adjacent to the p orbitals of the pi bond. And if p orbitals overlap to make a pi bond, then p orbitals overlap to make a pi bond. So this is what we call a conjugated system. 3 atoms or more. But in this case, we've got 3 atoms that each have a p orbital, and we define that as conjugation, an uninterrupted series of p orbitals. And because of that conjugation, the pi bond is not just between 2 carbons, the pi bond is between all 3. The pi electrons, the 2 electrons that make the pi bond, are there across all 3 atoms. And the radical is not just in one location, the radical is in 2 different locations. Jordan?
We could also count from the bottom and go like 1, 2, 3, right? And that would pretty much be the same structure.
Because it was symmetric, we could have placed the radical down here. Because it's symmetric, we could flip all of this. Yeah.
And then the bromine always adds where the radical is. Is there any?
The bromine always adds where the radical is. No exception. No rearrangements other than resonance. That might look like a rearrangement, but it's really just super cool.
And you said we always use bromine with these radical
Yeah.
products?
We'll always use bromine with radical reactions, unlike all of the others where pretty much anything is allowed. And to be fair, I've had those roadmap questions where I need you to do radical halogenation, and I've seen people do radical halogenation with chlorine. It's fine. But if I'm doing a multiple choice question, you're only going to see me do radical halogenation with bromine.
I swear this is the last question.
Chlorine is just too reactive. You can't control it as much.
So Thursday night, do you guys want it like as late as possible, or do you want it from like 6 until 8, or do you want it like 7 till 9? 6? Okay, 6 till 8, and then if possible we'll go later. I don't know. Okay, cool. I'll tell them 6 till 8.
Thanks, Johnny. Now go do some tutoring. Everybody that needs them is in here. All right. Let's tackle our next thing.
Possibility of 3 equivalences being on the final?
3 equivalences of what?
I don't know, anything?
Sure. There's one reaction in particular that can really benefit from 3 equivalences. Let's say I have something like 1,2-dibromoethane, and I expose it to 3 equivalences of a strong base. Well, the first equivalence runs 1 elimination reaction. The second equivalence runs a 3rd elimination reaction. The 3rd equivalence deprotonates my alkyne. I think that's the only place that you'll see 3 equivalences on the final. Oh, here's the jamboree. I don't actually know what that is about. By the way, oops, sorry, wrong class. I added a new module at the request of one of your classmates. Oops. And the new module is right underneath the final exam module. It's called Final Exam Archive. And it's almost all of my final exams. It goes all the way back to fall 2023. But use the ones that are more recent because I changed the way I deliver my course in 2024. So after spring 2024, you're going to see like multiple exams, multiple midterm exams. I used to give 3 midterms. So use those at your discretion. More practice problems, more chance to try things out. But you will notice that the older you go, the more different the questions begin to look from what I currently ask. Okay, so just another resource for you guys. I don't know why I've always limited my final exams. Anyways, let's look at this last fall's. Oh, I see. I uploaded the fall schedule. Yeah, that's where I thought I had uploaded your exam. That's crazy. Okay, question 10. Which is the correct IUPAC name of the alkene above? Our rules for IUPAC nomenclature: find the longest parent chain, the longest carbon chain that contains the highest priority functional group. Number it in such a way that the highest priority functional group gets its lowest locant. Organize the name with everything listed alphabetically. So our longest carbon chain, well, our highest priority functional group, the alkene. Our longest carbon chain containing the alkene, 1, 2, 3 carbons long. Pretty small. Considering there's a 5-membered ring, 3 is definitely smaller than that, but the 5-membered ring doesn't contain the alkene, right? So this should be propene, and I'm going to number it along this 3-carbon chain to get the lowest locant. So should I number from the right or from the left? From the left, because then I can get the alkene to start on carbon number 1. And that tells me where my substituent is going to be. My substituent is on position number 1. You'll notice that they all have some stereochemistry designation as well. So is this alkene a cis or a trans alkene? Transalkene. You can see that the low priority groups, the hydrogens, are opposite each other. So they must be trans. And really, the two options with trans are either number from the right or number from the left. And we'll number in order to get the lowest locant. Did you have a follow-up you wanted to ask on this?
No, you answered my question immediately because I was including the carbon that connects to the ring.
That is a super common pitfall, that this carbon gets added into the count. And remember, the way to recognize it is that a carbon cannot be both part of a linear chain and part of a ring. It's either one or it's the other, and this one is definitely part of the ring. Yes. The STEM Center, I think, maybe has my spring or my summer exam. Okay. You now have access to the spring one on that exam archive module I made. It works, right? Okay. Okay, good?
Wait, can I ask a question?
Yes, please.
So it's trans 1 cyclic into 1 propane?
Right.
Okay, the 1 propane makes sense. Why would it be cyclopentane?
Good question. Cyclopentane is a root. That's a parent chain. Cyclopentane has a suffix. Cyclopentyl, I mean, I guess it also has a suffix. It has a suffix that designates it as a substituent. And it is a substituent to the propene chain. Good question. So it wouldn't be cyclopentane 1 propene any more than it would be, let's say I had methyl cyclopentane. We wouldn't call this compound methane cyclopentane. Methyl cyclopentane. The substituent will get that YL. Good question. Allie?
There was no alkene, then that means that the cyclopentane would be the parent chain, right?
Yeah.
And it would only be the ring, you wouldn't like count it and then try and include the rest of it, right?
Yeah, so your question is, what if I make this modification? What does the name become? Now the longest parent chain is 5 carbons, no highest priority. 1, 2, 3, propyl cyclopentane. Exactly. And you're right, you don't count through it because, again, a carbon can't be both a part of a chain and a part of a ring. It only gets to be one, so we'd make that cutoff right there. Good. Vivi. If you called this one, or if you called this 1 methyl cyclopentane, no, I wouldn't, because it's not wrong. If you called this 5 methyl cyclopentane, I would. If you called this 2 propyl cyclopentane, I would take off points. Because if you're going to add a locant when there doesn't really need to be a locant, it better be the right locant, which would be the lowest possible locant. Good questions. Okay. Question 27. There we go. We were just talking about some of this stuff, right? Not on that. The allylic halide intermediate shown above is one possible product, the kinetic product. Which of the following is its structural isomer? I think I should have said the thermodynamic product. Wow, that question looks so familiar. And I'm sorry for those of you that I'm kind of spoiling some of these questions on the practice final. So if you still haven't tested it yourself, if you're still planning on sitting down and timing yourself and going through it, you've got a couple of layups. I form an allylic halide. And as we mentioned earlier, allylic halides form in these 1,3 allylic isomers. So wherever the halogen is, the alkene shifts up to there. Wherever the alkene is, the halogen shifts over. Or, someone mentioned this earlier, always, where the halogen is where the radical will be. Or where the halogen is where the radical was. So once you draw in that radical, maybe then you can see the resonance that is allowed a little bit more clearly. It depends on how well you feel with resonance. But this is just identifying the allylic isomerization, the radical being in two different positions. So what would you say? If you're seeing the kinetic product, which of the ones on the bottom would be thermodynamic? Allie says B. Jordan says B. Now, we didn't talk a lot about thermodynamic and kinetic, but do you guys remember the difference between the two? If you say one is thermodynamic and one is kinetic, you wouldn't be wrong.
One takes more energy to do, but is more stable after.
Good.
Or the other one takes less energy, but is less stable.
Exactly. One takes more energy and is more stable in the final end. One takes less energy but is less stable. How can you remember which one does which?
You gave us 2 ways to remember it, and I don't remember.
The highest highs and the lowest lows. Dynamic. That's the most dynamic one. The thermodynamic product requires the most energy but gives off the most energy. And the kinetic is the one that you provide just barely enough energy for it to overcome the lowest activation barrier. So I want you guys to think about these two alkenes, and I recognize that they're not in super plain view of you all, but I'd like you to look at these two final products, and can you tell me why is it that this is a thermodynamic product? What is it about this product that is more stable? That's what thermodynamic products have in common. They're more stable than their kinetic isomers. So why is this more stable?
Because the alkene is more substituted.
Alkene is more substituted? More substituted alkene, more stable. And Jordan, what is the substitution on this alkene?
Tertiary?
We won't use words like primary, secondary, tertiary, but close. What's the substitution of this alkene? 4. And the word we use for it is tetra. Tetra substituted. It's not mono substituted or di substituted or tri substituted. It's a tetra substituted alkene versus mono, di, tri, or tetra. This one's tri substituted, less substituted than tetra, so less stable. Okay, so that explains the difference in the final products. The alkene is more stable, so because it's tetra substituted, so it's the thermodynamic product. But why is its transition state higher energy than the other transition state?
What about the bromine? Because the bromine is more substituted in the
Great question. It has nothing to do with the bromine. The bromine being attached to a primary carbon versus a tertiary carbon doesn't change its stability very much. But the alkene, having 3 carbon groups bonded against it versus 4 carbon groups, that does have an important impact on its stability. Good question.
The intermediate radical, the one on the 3 is more stable, so it's kinetic.
Good. So here we have what substitution carbon radical? Yeah, a secondary carbon radical, which is less stable, higher energy, than a tertiary carbon radical. A tertiary carbon radical forms more easily, but as we're showing, in this case, it forms a less substituted alkene versus a secondary radical but it forms a more substituted alkene. Oops. That's the distinction between thermodynamic and kinetic. A higher high and a lower low versus a lower high and a higher low. Super simple. Notice how we've talked about this kind of stuff, but the wording of the question doesn't require you to necessarily know that stuff. If you do know the distinction between thermodynamic and kinetic, it just gives you a leg up because you know that this tri-substituted alkene is kinetic. The thermodynamic must be more stable. It must be more substituted. But you don't need to know that because you know that this reaction has a radical intermediate and you can identify the radical resonance forms that can form different products. There's a lot of different ways to tackle this problem.
So with the kinetic product, you see?
The kinetic product is given.
Oh.
I can see how C could be like a different kinetic product, but no, this is the one that it tells us to reference.
I was just thinking because the alkene is not, well, I guess it's still attached to the tertiary carbon. Never mind.
You're not far off there. Very close. Okay. Question number 31. Which part? Was this your question?
This is mine.
This was yours?
All of it.
All of it.
That's my question. Like, what's your thought process when you see this? Because I don't think anything when I see this. So,
You get sick. My thought is, how can I traumatize them enough to make them regret signing up for this class? No, my question is, or my thought process is, show me that you know how to do chemical transformations. You know those diagrams that I've been giving you all semester? These are snippets from those diagrams, essentially. And taking those diagrams, you know how we showed an alkene going to an alkyl halide? Well, we could have also shown an alkyl halide going back to an alkene by elimination, or an alkene going to a dihalide, and a dihalide going to an alkyne, and an alkyne going to a ketone. And all of our different reaction diagrams on those worksheets, you can butt them up next to each other and you can actually find a road map through all of those different reactions. That's what we're doing here. How many reactions did we learn with alcohols? I think 5. We saw that we could transform them into tosylates. We could turn them into halogens. We could do elimination on them with acid catalyzed hydration. So this is just starting at the alcohol and showing 2 of the 5 different ways that we showed how to convert with alcohols. And most of the roadmap has you fill in 1 step at a time. Also, I do my very best to make sure the roadmap is split evenly between predicting reagents and predicting products. So it's almost always an even number of points, and it's an even number of, or It's the same number of products and reagents that you're filling in. So from ethanol, do you know how ethanol, well, first of all, you have to know the structure of ethanol. Not hard to reason out though. 2-carbon chain with an alcohol. Do you know how ethanol will react with sulfuric acid? And do you know what to react ethanol with to substitute it for a bromine? And there's actually 2 different answers that you could use there. If you're not sure how sulfuric acid reacts with an alcohol, do you recognize this reagent? Because that can give you a clue about what functional group comes before it. OSO4, what did we use that with? What reaction was osmate used in? It's not to split. I think you're maybe thinking of the ozone reactions, O3.
Substitute, like, to eliminate it?
It doesn't run elimination or substitution. It's a syn-diol addition, so it lets you get 2 alcohols on a face of a alkene. This is an alkene addition reagent. So what functional group do I need to have before this? I must have an alkene. So even if you're not confident about how alcohols react with sulfuric acid, if you're any part confident about what OSO4 reacts with, you know that alcohols and sulfuric acid must form an alkene. What I like about these is that you can really start wherever and work your way forward or backwards through the rest of it. But I can see how it would be daunting. You take one look at it and it looks like it's all interconnected. You have to take it one bite at a time. Start wherever you want. You can kind of see how this one goes in 2 different circles. So I imagined you starting at the top. But there are others that I have had start on the sides. There are others that don't really necessarily go a specific direction.
You care to like draw out the structures of names, like
Oh, you could totally draw in the name, or draw in the structure for the name I gave. Totally. In fact, there's a lot of blank space on here, and it's all your space to use however you want. I will say this roadmap had some flaws. I think this reaction on the right-hand side was the biggest flaw, which was I had just taught students about the Diels-Alder reaction with the S26 diene, and then I gave them this, and they were like, yeah, Diels-Alder. But based on the product that you get up here and the fact that another reagent is added, it's not a Diels-Alder. It wasn't meant to be tricky, but it kind of came off as tricky. Another challenging part about roadmaps is that I do like to have you form multiple things and then have them react with each other. And that can be confusing sometimes. So as you go through the archive and you practice on your roadmaps, you'll see these dotted boxes, which are meant to kind of say, run these together after they form, run a reaction and predict the product.
So that's not saying this forms both of these.
Correct. This arrow is saying this reaction forms this product, which then reacts with this other product up above. Yeah, I find roadmaps to be fun. I find them fun to make, fun to grade.
So
Oh, well.
add in the reagents there, like in that box? Is that what you're supposed
Not in the dotted box. You need to draw the product from this reaction and then show how it would react with this. Oh, I forgot I gave this structure. Actually, it's not as bad as I thought. It's a lot easier. That's a fun looking structure though, right? And you'll have to figure out after you form the alkene and then do diol addition and then react it with this diene, what reagent is missing? What reagent would take the diol, the diene, and give this cute little product down here? Sorry? Are you trying to fill in the reagent right now? Do you notice You notice a chemical that's in the final product that's not in the starting materials. Can you identify the relationship of the functional groups that are in the final product? This is one thing that I think in the future semesters, those diagrams I give you, you guys were just giving me feedback about this semester. Maybe it was my OChem 2 class. Those diagrams I give you, those are new, by the way. I didn't used to put those on sheets. That's just from the fall. I think in the future, I'm going to give them fully filled out. Was that you that were talking to me about this? And not have you copy them down, which is like, copying them down is the part where you start to learn them. But instead, give them to you as a tool and then just have you apply them in a bunch of different reactions. But I want you to recognize the regiochemistry. Do you know what functional groups are in this final product? Ethers are in them. What else? Alkyl halides. And what is the structural relationship between the ethers and the alkyl halides? If they're 1, 2 to each other, they're in the same vicinity, and we call them vicinal. And that is the relationship that you get when you take halohydrin addition or haloether addition. You get vicinal haloethers or vicinal halohydrins. A confusing little molecule at the end, but it has all of the characteristics of the alkene addition reactions that we learned. Can I give you more? What other thoughts or concerns do you have with this?
I don't know. That was very helpful.
Yeah? Allie?
I feel like looking at that, I struggle to just like be able to look at a reagent and be like, yeah, it's gonna act like this, because I would go to my notes and be like, where's H2SO4 to see like which reaction mechanism it would apply to, but then when it's not there, then I'm like, oh wait, so what does it do?
So you look at the H2SO4, and you look at all of the different reactions where you use H2SO4. Is that what you're saying? And I think there's only one reaction that I gave you guys where H2SO4 was the acid written. And that was, okay, no, a few. Alkyne with HgSO4 and H2SO4. And then alcohol with, yeah, and H2O. And then alcohol with H2SO4.
But that's not an alkyne, so how do you work?
Well, it's not an alkyne, it's an alcohol. What I would say is you should look at what functional group you have and recognize what this reagent will do with that functional group. Right? You guys having access now to all of my past exams, you should really go do the other roadmaps. Do as many as you can, because no two are alike. And it will at least give you a feel for how to analyze them. I realized I skipped over some questions. Questions 22 and 23 on arrows from before. But Vivi, that was from the spring exam, right? The one that you're looking at. Didn't you ask about questions 22 and 23? 32 and 33. Okay.
Yeah, it was on the spring one.
Oh, so they were multiple choice questions. Well, let me do this quick. Mechanisms to know. What mechanisms will I be grading you on?
It's the same thing on both of them, pretty much.
It's just the arrow pushing.
Yeah.
Okay. And that's what you wanted to know out of it, was which arrow pushing will I be expected to show, not how do I solve the ones that were on there?
Yeah, just kind of going over arrow pushing, but all
Sure.
tips and tricks and
So you'll have mechanisms from Unit 4 and Unit 5. From Unit 4, there are a selection of alkene addition reactions. HX addition, keep in mind it has a carbocation intermediate. And acid catalyzed hydration, which has a carbocation intermediate. Why do you need to be wary of a carbocation intermediate in a mechanism? It doesn't necessarily mean that it's not if it's an alkene addition, but you are right that SN1 and E1 both have carbocations as well. Much like with SN1 and E1, it could rearrange. That carbocation might have a methyl group shift. It might have a hydride shift. And if it does, you need to show it. That's what you have to be wary of with carbocations. You need to know the mechanism for X2 addition or X2 in alcohol or X2 in water. And so remember that these are really the sets. The alkene addition mechanisms that have carbocations, the alkene addition mechanisms that have halonium rings. None of the other alkene addition mechanisms. You don't need to know the mechanism for ozonolysis. You don't need to know it for hydrogenation. You don't need to know it for diol addition. You don't need to know it for epoxidation, although that one's fun. You don't need to know it for a lot of different things, just these. Then from Unit 5, I'm not going to ask you to show me mechanisms for alkyne reactions, because if you can do an alkene mechanism, you can do an alkyne mechanism. You just do it twice as many times. So it's substitution and elimination reactions that you need to know. And this is harder to lay out quite as cleanly. I'll be honest, I don't like the terms SN1 and SN2. There are a number of nucleophilic substitution reactions that are first order and second order. Grouping these all as being super similar to each other, I'm not a big fan of it. Anyways, generally, carbocation intermediates, not generally. SN1 and E1 always have a carbocation intermediate. SN2 and E2, generally one step, strong base or a strong nucleophile, making the changes all at once.
So you say that, and then sometimes there's like the acid base thing at the end. Is that another step?
Yes. Yes. So I do say that, and if there's a deprotonation at the end, that might add to the number of steps.
So in that, you would draw like another arrow and say like this is what happens with the acid base.
Correct. Correct. So you can never say that SN2 is one step. Just can't say it, because if you do need a deprotonation, that adds to the step. But you can always say that SN2 is a backside attack. What do we mean when we say a backside attack? The stereochemistry inverts. And that's because of what I had drawn earlier. The nucleophile has to attack the carbon directly opposite of where the leaving group is. I just saw a word over the weekend called the Walden inversion, and that is the idea of your leaving group inverting the stereochemistry when a nucleophile comes in. And there's this transition state in between the change when the leaving group is leaving and the nucleophile is coming in. They call the Walden inversion. It kind of looks like an umbrella getting blown open and then folding back into an umbrella in the opposite direction. That ever happened to you guys? Your umbrella caught by the wind and your umbrella pointed the opposite way? Has it really? You guys are not good at holding your umbrellas. I don't think so. Maybe I just buy strong umbrellas. Well, you've all lived through a Walden inversion, is what that means. The wind did a backside attack and did SN2 on your umbrella. Maybe I just don't use an umbrella enough. That's what it is. Okay, E2 also requires something stereo-specific, but what it requires is the anti-planar or the anti-periplanar beta hydrogen elimination. It will only take a hydrogen adjacent from the leaving group if that hydrogen can be directly opposite. And we spent some time with that last week. I think you guys came to understand you have to be able to look at the stereochemistry of the leaving group and the beta hydrogen. Okay, so those are the mechanisms. You wanted to spend some time on arrow pushing, right? So I have a problem. We'll do some arrow pushing on, but then we'll also use it to look at whether it's an SN1 or an E1 reaction. So I want to take 2-chloro 1,1-dimethyl cyclohexane. And I want to get 1,2-dimethyl cyclopentene. Did I say cyclohexane? Sorry. It would work on there too, but I meant cyclopentane. What type of reaction am I running? E2, elimination. Do you guys agree that it's E2 or elimination? Definitely agree that it's elimination, right? Is that hard? It is elimination. How do we know it's elimination? We form a pi bond. And that's what we said elimination reactions are. Why, Jordan?
Well, there's a methyl shift, right? So that means that carbocation would form an aldehydes.
Perfect. So Camilla, do you concede that it shouldn't be E2? But what drove you to say E2 right away? You knew it was elimination right away. But distinguishing between what type of elimination, that was the challenge. Do you guys see that? I think for a lot of you, recognizing it was elimination was not hard. But being able to spot whether it would be E1 or E2, especially since there's no reagent listed, that makes it even harder. But the methyl shift is the only indicator. The fact that this methyl group moves means there must be a carbocation intermediate. And E2 has how many carbocation intermediates? 0. Only E1. So I need to choose a reagent that will not do E2. And again, I don't really like the name E1 and E2. I haven't figured out what name I would have given it if it were just up to me. But I maybe would have called it strong base elimination versus weak base elimination, because that's the distinguishing feature of E1 and E2. A strong base wants to take a hydrogen, and it is the driving force in the elimination. A weak base doesn't want to take a hydrogen, and it will wait until there is an intermediate that is reactive enough. It's already at a higher energy, and then it will do elimination. I need a weak base. I need a base that will not eliminate until after a carbocation has formed, because that will allow for the methyl shift to occur. So could I use something like hydroxide, NaOH? Why not, Jordan? Hydroxide is too strong. Hydroxide wants to do elimination, and it will eliminate E2 without a carbocation. Could I use ethanol? Could I put ETOH over the arrow? So yeah? Annie says no. Jordan says no. Christine? Do you want to share why you say no?
Correct me if I'm wrong, but wouldn't that also leave OH? Or
Ethanol,
am I thinking about it wrong?
alcohols are precursors to ethers. So ethanol as a reagent will never put OH onto the molecule.
Okay.
It might put OET onto the molecule,
Okay.
but it won't put OH. And I think we can get around that by saying heat, because heat drives elimination. So now we're not looking at ethanol as a nucleophile, although it can be. Now we're looking at ethanol simply as a base.
I think the confusion might be the difference between ethanol and like sodium hydroxide. Because sodium hydroxide, the OH would act as a hydroxide ion, whereas with ethanol it doesn't.
Ethanol does not act as a hydroxide ion. Is that? You're right. No, I do like what you're saying. Talk to me more. If I say I'm adding something like NaOH, I'm actually thinking about OH minus.
Whereas with ethanol, you're not. Because like you said, ethanol would create an ether.
It can still be a base though, too. Both of these are bases. Ethanol is a hydrogen ion acceptor. Hydroxide is a hydrogen ion acceptor. Jordan, do you want to say why you think no, ethanol might not work here?
I was kind of thinking along the same lines as her, and maybe I was thinking more substitution where it leaves like an OH or like H2O, and you would have to do that. But I think we could even use water.
Yeah, and do you know the difference between water and ethanol? It's just a small carbon chain. Water is inorganic alcohol. Water is very similar chemically to all of our alcohol groups. So if you would have used water here, then you could use any alcohol here too. If we had hydroxide, and again, secondary alkyl halide means we might see competition. There is a rule I didn't tell you guys about called the neopentyl effect that says SN2 is forbidden adjacent to a quaternary carbon, but I'm not going to ask you about that. So we couldn't do SN2 here if we wanted to, but let's say that we added heat because we really wanted to drive elimination. I think you guys would agree that this elimination would be E2. It wouldn't wait for a carbocation and it wouldn't rearrange. It would take the only available beta hydrogen. But I need to do an elimination. I need to do a rearrangement. So I need a carbocation. So I need something that will not deprotonate right away. Ethanol works well. Water works well. Methanol works well. I know on that table I gave you guys that chloride is included in there as well. I don't know of anybody that would try doing this elimination with chloride, but I guess in theory you could do it. But ethanol, super cheap solvent. We've got loads of it in the stock room. It would be easy to run this reaction.
If we put chloride, would we get it wrong?
No. If you put chloride, I would give it to you because I have definitely given you that as one of your weak base, weak nucleophiles.
If we were doing substitution
I think you sound like you're talking about alkylation.
Like HOCH3, we did that.
You want to see the mechanism?
Right? I don't know what it
Say it again. We did SN1 with a HOCH3, methanol. Yeah, because SN1 and E1 are generally in competition with each other. If a reaction can do SN1, it's just a small deviation away from doing E1. Methanol here can run E1. That's why we had to provide heat to make sure it didn't compete with SN1. I think what you guys are getting confused about, though, is you were looking at ethanol being added, and you suspected it might add an OH. Where did the ethyl chain go? Somewhere in your prediction of bonds that break and form and break, you're saying that I should break the carbon-oxygen bond. That's hard to do. And it's hard for me to get that across that it's hard to do, because the most I can say about it is like, that's hard to do. And then you just have to remember and accept that. And I understand why you see ETOH and think, I should put an OH there. But in doing that, you're trying to cleave the carbon-oxygen bond. And is it leaving as a carbocation? Because you know the carbon-oxygen bond is owned by oxygen. It's not doing substitution, so what is it doing, right? I want you to think rather, OH, that's an easy bond to break. After it gets put onto the molecule, this group is ethanol bonded to the molecule. That's an acidic oxygen. That just donates its hydrogen, right? Let's look at the mechanism for this, shall we? Let's see how this occurs. You guys are okay with this list of reactions? And did I clarify enough, Jordan and Allie, about the distinction between SN1, SN2, E1, and E2? Do you feel good on that? Like here, how did we know it was E1? The rearrangement. We can look more at substitution as well. All right, what is the first step in this reaction mechanism? Anybody? Bromine leaves. Leaving group leaves. Another way of describing that first step? Anybody? Instead of saying leaving group leaves, anything else I could use to describe what happens in the first step? This step is not an acid-base reaction, unfortunately. But a lot of our reactions did start as acid-base. We could describe this step of the reaction by what forms? Sorry? Oh yeah, heat. Thank you.
And that leaves on its own. It's not ripped away by the nucleophile or anything. It's just like molecules bumping in it, right?
Yeah. Yeah. Oh, I was driving down the road the other day and I saw a guy ahead of me. Hazards were on. Driving kind of chaotically between like the shoulder and then back into the lane as if he wanted me to pass, but he was going 35 or like 30 and a 35. Like, he wasn't going slow enough for me to pass him. I was like, why is he doing this? And then I noticed his back right tire was just like all over the place and looked like it was just ready to roll right off. That's basically what's happening here. This molecule is just getting bumped around. It's got a weak bond, and it gets bumped around in just the right way, and Reactive intermediate forms. You guys, like, I'm serious. This is a car whose tire is about to fall off. It's no different. It just needs that activation barrier overcome, and then it happens. What's causing this? Nothing. It just has enough energy to do it. So we could call this step leaving group leaves. We could call this step carbocation forms. And it is similar between SN1 and E1. They share the same first step. Now, this is what I call 1A because it doesn't always happen, but if it happens as a result of step 1. And what is 1A? A rearrangement. So here, a methyl group shifts over to the carbocation. Why don't I have an arrow showing me where the carbocation is going to be? Nice. Electrons move. Positive charges are like gaps in the line at Lagoon. That gap in the line isn't going to leave the line and go be a gap somewhere else in the line, right? You are going to move into the gap in the line and leave behind you a gap where you were. So I have an arrow starting from where the methyl group is and moving it to a gap and leaving in its wake a new gap. Yeah, light bulb click. And that's how all of these positive charges are. Do you guys remember on your midterm, I gave you this step and I gave you the arrows. Chloride moves into that gap. No other bonds should form, no other bonds should break, but I should fill the gap. In this case, I'm actually just pushing the gap, right? But in this case, I am consuming it. Okay, so here's my methyl shift. And now I need step 2, which is beta hydrogen elimination, or I could call this just elimination. This is the carbocation rearrangement. I fear I've run out of space and I should really just move it over here. On the exam, true or false, I will give you full credit if you show elimination with either ethanol or bromide. True. Which of them is more likely to serve as the base in the final step? Ethanol is. Just based on pKa, the conjugate acid of ethanol is far less acidic than the conjugate acid of bromide. So it is more likely that ethanol is the acid, is the base, but bromide could be a base, so if you show it, I would accept it. True or false, this one's for Hamza. True or false, I could take any hydrogen on there and form the alkene. Which one do I need to show? So that what you're saying is true, there's a specific hydrogen it needs to come from.
Yeah.
You want to tell me where?
The one for each one?
Here? Will that form the alkene that I want?
Oh, sorry, my bad. The other one. Yeah, like that adjacent to it. Yes.
Here,
Yeah.
up here. This hydrogen should still be present, right? CH3 in the final product, I want to keep that as CH3. But do you see the change needs to occur on the carbocation? Something needs to change there. And adjacent to it, this carbon doesn't look like this just yet. there is a hidden hydrogen. There's an assumed hydrogen on that position. And that's the hydrogen specifically that we need to take for this elimination. Look at where your alkene forms. Make sure that you're drawing it from that position. I want to say there were maybe a third of the elimination mechanisms that I graded today showed elimination from the wrong hydrogen. Some were possible hydrogens that were just the wrong carbon. You went from the more substituted rather than the left. Some were hydrogens from carbons that were super far away. So when you're running this last step, this beta hydrogen elimination, try and figure out where your alpha is. Right now, my alpha is the carbocation, and beta has to be adjacent to that. And map yourself relative to the final product. If this is where alpha is, and that's in the pi bond, this must be where beta is. It also has that methyl group. So ethanol or bromide serves as the base. CH bond breaks, fills the carbocation's gap, forms an alkene, and the mechanism is done.
Also, the carbocation, it doesn't have a hydrogen to even get, right? So that we can think of it that way too.
You're right. I mean, I couldn't take a hydrogen from that carbon even if it had one. For instance, if I had something like this, that carbocation has a hydrogen on it, but I can't eliminate that hydrogen. There's nowhere for the electrons to go. This carbon has a full octet, that carbon has a full octet. How would I form a pi bond? In fact, I want to form a pi bond with that carbon by getting the electrons from an adjacent carbon. So even if the carbocation carbon has a hydrogen, the carbocation is alpha, look for a beta hydrogen.
And the carbocation is always alpha.
That's a good way to think of it. The carbocation will always be alpha.
With the oxygen, now with the positive charge on it,
Yeah.
does it need to be deprotonated, right?
Yeah, I mean, if it was deprotonated, it would get deprotonated by bromide,
Right.
which would form HBr, which I could have shown. I could have just shown bromide forming HBr. But if you have HBr, which you shouldn't because it's hard to store, and you put HBr into a bottle of ethanol, you wouldn't have HBr. It would protonate all of the ethanol. So you're right. This mechanism is done. You don't have to show anything else here.
Because I think that's the step that we were missing last class. Because there was a piece where you were like, well, you didn't finish deprotonating it, so I didn't know if that was.
Oh.
Do you know what I'm saying?
Oh, yes. You were showing a substitution. So you were showing something like ethanol adds on, and then the H needs to be pulled off.
Because it's being substituted.
Right. Now the H is removed. You're welcome. Okay, when we come back on Wednesday, we will fix those alkyne reactions. Sorry, I should have just done that today. And finish our questions on the final. Come with more questions Wednesday. Have a good night. Happy studying.